let's continue our discussion about wave equation solution for material medium. So let's start review some of the propagation characteristics associated with electromagnetic wave propagating within medium. So first is the relationship between propagation constant gamma and the material properties, including the permittivity, permeability, and conductivity. So as you can see here, the product of j omega mu times sigma plus j omega epsilon equals to alpha plus j beta to the square, the attenuation constant alpha and the phase constant beta. And according to the real part and imaginary part of the square part, we can have association between like this. And using this relationship, we can reorganize the alpha and beta term and have the result of alpha to the square plus beta to the square equals to omega to the square times this thing, the equation 4.93. And using 4.93 and 4.92, we can have solution for alpha and beta, that is these things. And it looks a little bit complicated, but as you can see here, it all involves with properties such as the material property, of course, the sigma, the epsilon, and mu. However, they also associated with what? With the frequency, omega. So they are, in fact, the combination of frequency, permeability, permittivity, and the conductivity. And their form are not that different. So as you can see here, the second thing is the same, while the first term has a difference in the minus sign and plus sign. And of course, it looks a little bit difficult, but they can be, of course, they can simplify later. We will look into that. And here we have the solution for alpha and beta. So a few observations can be made here. First is the cause for non-zero attenuation constant for non-zero alpha is what? Is the conductivity. So conductivity is the source of signal attenuation. So for these two equations, if you set sigma to 0, then you have a 0 alpha and a non-zero beta. If you set up sigma as 0. And also, this equation suggests that the amount of attenuation is kind of proportional to this term, sigma over omega epsilon. So this term is referred to as the loss tangent is proportional to the conductivity, it's inversely proportional to frequency, and is inversely proportional to permittivity. So they can be, so in practice, in application, we usually use loss tangent to describe, to specify the lossy property, lossy characteristic of a medium, all right? And so as you can see from the previous equation, we know that material properties, even though that for now, it seems to us that a sigma, epsilon, mu are constant. Say the epsilon sub-zero and mu sub-zero for vacuum space is 8.854 times 10 to the minus 12, something like that. It looks like a constant, but in fact, they can be, or they are in general, function of frequency. That is, the amount of conductivity, permittivity may change at the different bands. So Even though that we describe that they are functions of frequencies, but they are not that sensitive to a little frequency change. We can say that they are mostly constant in a certain band, say in the microwave band. They may, the permittivity, say the permittivity of a printed circuit board can be a value, can be 4 in the microwave band and can be 3.9 in the millimeter wave band. So they are not the same at a different frequency. But in practice, for most users, if your interested frequency band is confined in a specific range, then in general, a constant is enough to describe the general behavior of the material in this band, all right? So most likely we can still say that the loss tangent or the permittivity are constant for a particular band, say microwave, millimeter wave, or tetrahertz, or infrared. In individual frequency bands, they can be constant, and the number can be somewhat different in the optical band and millimeter wave band. They can, if the band frequency difference is very large, then the number can be different. All right, and here is the expression for phase velocity, Vp. So P is in fact represents the subscript P is in fact refers to phase. So this is the so-called phase velocity, which is defined as omega, the angular frequency over phase constant, omega over beta, and they can be represented as this number. As you can see, this thing, the phase velocity is also associated with the loss tangent, which means that if the loss tangent is non-zero, if the conductivity is non-zero, then what? Then the velocity of phase velocity can be a different number for different frequencies. All right? Omega represents the difference in frequency, and sigma represents the conduction current, the conductivity. And to put it a more simple way, if we set sigma to 0, then what? If sigma is 0, then Vp is a constant, that is 1 over square root of mu times epsilon, that is 3 times 10 to the 8th, or something like that, like the speed of light, for all frequencies. In vacuum, the microwave, the millimeter wave, the tetrahertz, the infrared, the optical wave propagates in the same speed. However, if the electromagnetic wave is propagated in the medium with non-zero conductivity, then what? Then the propagation velocity is different for different frequency. All right, so the most famous experiment that we have ever seen on the history of physics is this one. Do you know who did this? Newton, right? 牛顿嘛，牛顿的那个三棱镜，那个年代的那个科学家都是多才多艺的，什么学科都会的，所以牛顿除了力学以外，他在光学上面也跟人家搞得轰轰烈烈，OK，你应该有听过那个光的那个二元性的嘛，他跟虎克他们还是谁，杨格他们吵得不可开交嘛，所以，牛顿是粒子派还是波动派？牛顿是粒子派的，OK，all right, so according to this equation, we know that electromagnetic wave in different frequency will propagate in different speeds due to the presence, due to the non-zero conductivity. And this causes the so-called dispersion. So this phenomenon is called dispersion. That is, waves of different frequencies propagate at different speeds, so that the refraction angle are different. They propagate in the different speed. And another important conference associated with dispersion is signal propagation in communication system. For example, we know that a square wave can be decomposed into f sub 0 plus a set of F1 okay, F3, if it's 3 times higher order mode, and what time, 5, and etc. Okay, so we know that using the cosine series, you can represent square wave as the superposition of a cosine series. And because of dispersion, which is shown in the slide, we know that the wave, as it propagates, no matter within the air or within cables, 不管是有线或无线的, because the propagation speed are different, the amount of attenuation are different, then in general, high frequency components attenuate greater and quicker than lower frequency ones. So as a result, with a certain distance of propagation, the original square wave will decompose into more sinusoidal-like waves because only the lower order terms retains while higher frequency terms are attenuated. So that's an inevitable phenomenon that we observe for wired and wireless communication. So that's one of the important issue. If you are doing wireless and wired communication systems, right? So this is the so-called dispersion. And here is the representation, the equation for the wavelengths by considering the loss tangent. So you see the loss tangent also involved in the expression for the wavelengths within the medium. And because the attenuation introduced by the non-zero conductivity, so if you are checking the wavelengths of the signal, conventionally, we are looking at the position, say the maximum. Conventionally, we usually check the maximum position. If they reach the same amplitude, then we can say this is one wavelength. However, considering the presence of attenuation, the signal will become smaller and smaller as it travels. So the definition should be modified because the peak, the maximum value, will become smaller and smaller as it propagates. So the definition for wavelengths should be changed to checking the zero crossing interval, which will be more convenient to define the wavelengths. Next is the parameter eta. So as we already mentioned, eta is what? Eta is the so-called intrinsic impedance. Even though that the unit for eta is what? Is ohm, which is the same as a resistor. But the eta, the intrinsic impedance for propagating electromagnetic wave, is not a resistor. It's the ratio. It's a representation for the ratio of the electrical field intensity over magnetic field intensity. All right? And for a lossless case, for electromagnetic wave propagates in free space, the eta is a real number, a pure real number. However, if we take into account the loss tangent, the non-zero conductivity of the medium, propagating medium, we have the ratio of electric and magnetic field is the ratio eta is not a constant. So as you can see here, eta becomes what? Becomes square root of j omega mu over sigma plus j omega epsilon, which is not a real number. It's for non-zero conductivity sigma, it's a complex number. Of course, you can take the magnitude of the intrinsic impedance to show that, the electrical field is how much larger than the magnetic field intensity. However, the complex number property of the intrinsic impedance also suggests that the electrical field intensity and magnetic field intensity has a phase difference. For free space, they are in phase. They have no phase difference. On the other hand, for wave propagating within a material, they have a phase difference, a few degrees, several degrees, things like that. So you need to account for the phase difference for E and H field if you are working with wave propagating in the medium. So they are the propagation constant and the intrinsic impedance of the medium, right? And the equation 4.100 is also interesting. And it suggests that we characterize the EM property of material by sigma, epsilon, and mu. And the wave properties can be found out or can be measured or estimated in terms of the propagation constant and intrinsic impedance. So in this equation, in this set of equations, you can see here we try to represent sigma, epsilon, and mu in terms of gamma, eta, and omega, right? And the one interesting thing about EM property of material is we usually don't know the number for sigma, epsilon, and mu, right? In fact, in general, we don't know the epsilon, mu, and sigma over material. Then your question is, then how do we know what value is sigma, epsilon, and mu? Well, you can perform some measurement about the electromagnetic wave propagating in this medium so that you can use the measurement result to find out gamma, eta, and of course you know the frequency omega, which is controlled by your signal generator. So once you perform the measurement, you're using the result to derive eta and gamma. Then you can use eta, gamma, and omega to estimate sigma, epsilon, and mu of the material. All right. So in practice, the material, the EM property of the material is estimated using measurement result. They are not a given. All right. And here we see. So number 6 also related to the dispersion phenomenon, saying that non-sinusoidal signal can be decomposed or can be synthesized as a summation of sinusoidal signal in different frequencies. All right? Then, because of the dispersion characteristic, dispersion property, the non-sinusoidal signal, the different frequency component of the non-sinusoidal signal as it propagates will experience different phase velocity, different attenuation level. So after all, with a certain distance of propagation, the resulting signal will look different from the original one, because higher frequency experience more attenuation and the lower frequency content experience less attenuation because of the dispersion property. So now let's take a look at some examples. So example 4.5 shows the material property of a certain food item. Well, in fact, this is kind of frozen meat. You can say that I guess the items that it refers to is frozen meat. All right, so it has a sigma conductivity of 2.17 Siemens per meter. This is a relatively high number, okay, which means this frozen meat have a certain conductivity. As for your reference, the conductivity of seawater, 海水, is about 4. So and seawater is already considered as a conductor. 海水是算是导体哦，电的导体哦。纯水不是导体纯水的那个导电系数还蛮小的，但是一般你的那个水龙头水都是因为有不同的有一些电解质，所以它是算导体啦，算导体所以只要淹水的时候啊，有那种电线啊，那个其实是你才会知道说有那个触电的那个危险那就要想办法减少你的那个身体上的那个导电系数或者网络上有一些小短片啊，教你说要怎么样，脚要怎么踩才能够减少那个触电的几率算有道理了他的我看一看他的讲法的意思是说，比如说你双脚要跟那个可能的那个电源电压源保持等距这样子的话，你那个你比较是站在所谓的 equal potential line 上，等电位线上面那个电位差小的话，那从你身上流过那个电流的几率就会比较小OK， 不是几率啊，电流的那个，即便有的话，那个电流量也不会太大了Alright, and so conductivity is 2.17. The epsilon, the permittivity is 47, which is relatively large, and it suggests that the food item contains some water. Okay, if you have some liquid, then its permittivity is in the range of a few tenths, which is much higher than ordinary solids such as wood, stone, or ceramics. So 47 is a large number. It's a large number, but it's common for material has some water content. And mu is equals to mu sub 0, so which suggests this item is non-ferromatic, 不带磁性的 non-ferromatic. And at the varying frequency of 2.45 gigahertz, which is which is the frequency for most microwave oven, So we wish to find out propagation parameters such as alpha, beta, lambda, VP, and eta. So we simply substitute the three numbers into equations to find out the associated attenuation constant, phase constant, propagation constant, velocity, and etc. So this looks like a good example to put in the final, right? You simply knows the equations and you knows how to use the calculator, right? So if you did not perform well in the first two midterms, you are recommended to work on this basic problem to ensure now you know that what you are doing, all right? Then you will stand a better chance to perform well in the final, all right? So it's just simply you find out the correct equation, put in the number according to the specified frequency and the material property. And of course, you need to perform some transformation between polar coordinate, different representation of a complex number. So you need to change magnitude and phase into real and imaginary part, something like that. So be sure to work on this example yourself, okay? So the gamma, the propagation constant of this food item is 58 plus J 356. So it has a sufficiently large real number, real part. So what is the consequence of this result? If you have a large real part in your propagation constant, then it suggests you have a substantial wave attenuation. So the real part is alpha, the attenuation constant, and the unit is Nepper per meter, and the phase constant is the imaginary part, so beta is 356. The wavelength lambda can be found by 2 pi over beta, which is 1.7 centimeter. And for your reference, the frequencies that we are talking about is 2.45 gigahertz. What is the wavelength at this frequency in free space? In free space, which is about 12.5 centimeter, something like that. And what is the number? What is the wavelength we have here? Is 1.76. Why? This is much smaller, much smaller. Why? Because this food item has a relatively large permittivity, which is associated with what? With the velocity. Now, so yeah, let me calculate this thing. The velocity. For free space, what is the phase velocity in free space? 3 times 10 to the 8th, right? And here we only have 0.4 times 10 to the 8th. So it's about 8 times smaller. It only has a 1/8 of the velocity in free space. So because the velocity is much, much smaller, the wavelength becomes much smaller as well. All right, so this makes sense because you have a higher permittivity. And next, let's check up with the intrinsic impedance eta. And because this item, this frozen meat, has a non-zero conductivity, non-zero loss tangent, so the intrinsic impedance eta is not a real number, it's a complex number. So put in those numbers, you end up with a complex number as 53 with 9 degrees. So in this frozen meat, the electrical field intensity is still much greater than the magnetic field intensity by 50 times. However, the phase of the electrical field intensity and magnetic field intensity has a phase difference of nearly 10 degrees as a consequence. All right, so we shall conclude this section by generalizing the Poynting theory. So first, we substitute the conduction current J as the product of sigma and E, so that E dot J becomes sigma times E to the square. So originally, the Poynting theory equation can be rewrite as equation 4.101. It still has three terms, and as I already mentioned before, the first term represents what? The first term represents the power dissipated in the medium. The second term represents the energy stored in the medium in terms of electrical field. And the third term represents the energy stored in the medium in terms of magnetic field. So the last two are stored energy, while the first one is dissipated energy. And the Poynting vector in its instantaneous form can be expressed as the cross product of E and H. And we also, aside from the instantaneous Poynting vector, we are also interested in the time average Poynting vector, which can be used to indicate the amount of power dissipated within the medium. And it's, as we have seen before, the time average Poynting vector P with these arrows on the side can be found as 1/2 of the real power of E cross the complex conjugate of H. So the three terms in the Poynting theory now are referred to as PD, WE, and WM. As I already mentioned, PD represents the power, the energy dissipated within the medium. WE represents the energy stored in terms of electrical magnetic field, and WM refers to the energy stored in terms of magnetic field. So the very last example of this section is example 4.6, that is the power flow of a uniform plane wave in seawater. So in this example, we try to demonstrate that if you have electromagnetic wave going into seawater from air to seawater like this, what can we expect about the electromagnetic wave going into seawater? Well, what we can expect is the energy of the EM wave will quickly dissipate on the surface of seawater. That's the reason why submarine cannot use electromagnetic wave to conduct wireless communication. OK， 所以这个例题其实跟一个现实上面的应用还蛮有关系的，也就是说，潜艇在潜到海底下的时候，一般来讲啦，它大概没有办法用无线通讯来跟它的基地做联络，不过我跟你讲，只是大概，真的不行吗？完全不行吗？其实也不是啦，当然啦，那个船上、潜艇上面都有无线电通报机。那假如它浮在水面上的时候，露了个头出来的话，那当然那个无线电报发射机那个就，因为在空气中传播，那就不是问题了，一定有的， 那但到了水底下的时候，从这个例子，我们大概简单看一下，你会发现电磁波的能量进入到海水之后会被快速的衰减，大概水下面1、2公尺，大概那个能量全部都消耗掉了，所以一般来讲，传统上潜艇不太用无线通讯，但不是说完全不可能，实际上就是说，要么你用更低的频率，那要么就是什么？要么就学鲸鱼啊，有没有？听说鲸鱼的那个叫声给一些，因为它频率够低，所以听说是可以传上几千公里啊，上千公里啊，鲸鱼叫，有没有这么厉害我就不清楚了哈。不过至少那个 YouTube 的说书人是这样讲的哈。OK 哈。不过生物不是我的专业哈，所以有可能啊，理论上是没错哈。Okay, so let's go back to the problem. So suppose we have, so here we have the seawater property, sigma equals to 4 as I already mentioned, epsilon is 80, which is a common value for water in room temperature. One interesting about water is its dielectric constant, its permittivity varies as the temperature change. It's about 80 at room temperature. If the water is at a temperature of nearly boiling, say 100 degrees, the number can be reduced to about 40 or 50 something. So the permittivity in water or in liquid is in fact a function of temperature. And the permeability mu is equals to mu 0, as usual. It's a non-magnetic material. The incident electrical field is 1 times cosine phi times 10 to the 8 pi t. So what is the frequency? What is the frequency? Omega t equals to what? So omega here is what? 5 times 10 to the 4th pi. So, okay, 2 pi f. So if you divide it by f divided by 2 pi, it becomes 2.5 times 10 to the 4th, which is 225 kilohertz. It's a low frequency from nowadays standard, right? 25 kHz is relatively low from today's standard. But at the time of, say, Second World War II, no, it's not a very low frequency. So actually, you can have electromagnetic wave frequency smaller, even smaller. It's possible. So we would like to find out the instantaneous power flow at the different depths of within the seawater. So because seawater has a relatively large conductivity, it can be seen as a good conductor. And here is a simplified result for good conductor. For good conductor, the value of alpha and B are relatively the same, which is around square root of omega mu times sigma over 2. Well, in fact, we will have this approximation number in section 4.5. We will see that later. So put the number of omega, mu, and sigma into this equation. We find out alpha equals to beta, and they are equals to around 0.62A. And the associated intrinsic impedance is 0.222, and the angle is 45 degrees. And 45 degrees is true for most good conductors. For good conductors, the angle between E and H field is 45 degrees. And as you can see here, the intrinsic impedance is a number smaller than 1, which means what? means the magnetic field intensity in the seawater is in fact larger than the electrical field intensity by nearly 5 times. So in space, in the air, the electrical field intensity is 377 times greater than the magnetic field intensity. However, in seawater, the magnetic field intensity is in fact greater than the electrical field intensity. All right? So as a consequence, you can have the E and H field like this. And what is this number? Exponential minus 0.62 AZ. This is the attenuation part. So as you can see, as the Z becomes larger and larger, which means the wave goes in further and further into seawater, the E and H field will reduce, it becomes smaller and smaller. So here are the representation of E and H field. You will notice that the H field is 4.5 times greater than the E field, and they have a 45 degree phase difference, which is shown as minus pi over 4 in radian. And the cross product of the two shows you the instantaneous Poynting vector, like this. And this can be regarded as the product of cosine alpha times cosine beta. So the product of two cosine function can be simplified as 1 over 2 times cosine alpha plus beta and minus cosine alpha minus beta, blah, 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 like this. So use this relationship, this trigonometry, this relationship, you can find out the instantaneous Poynting vector can be rewritten as this, which has two terms in the middle parenthesis. One is cosine pi over 4 and a cosine blah blah like this. And if you taken the time average, the second term goes to 0. The average of the second term is 0, while the average of the first term is still cosine pi over 4, which is what? Which is cosine 45 degree, and it's 1 over square root of 2. So you simply divided 2.25 by square root of 2, and you end up with this thing. So this is the time average Poynting vector for electromagnetic wave going into seawater. So you can see that this representation. So at the sea surface, that is Z equal to 0, the PZ number is 1.6. However, if the depth of the seawater is 1 meter, then the PZ becomes 0.4, so only less than 1/3 of the power of the EM power at the sea surface. At the depth of 2 meter, then PZ becomes 0.13, which is less than 1/10 of the power at the sea surface. And this is an exponential function, so as the depth goes up to 10 meter, then the power, the time average power density Poynting vector becomes 5 times 10 to the minus 6, which is relatively small, right? So that should conclude